parallel session about conversion technologies from biomass to sustainable biofuels. I'm very happy and delighted to chair this session, and I hope the presenters will present very good stories about how they think about producing the sustainable biofuels. First out is Gerhard Muggen, Managing Director of BTG Bioliquids.
Thank you very much for the introduction. Yes, I'm going to tell a story. It's a story about pyrolysis, the successes we have achieved the last year, but also where we come from. Because it's a long journey. It's a story about where we come from, a story about being patient, making a lot of mistakes, because making mistakes also means that you build up experience. So I'm going to tell you in this introduction, I'll go through, of course, in the future, but I will start in the past. First, who we are. We are a technology provider, and we consider ourselves as a product leader in this field. We're one of the few companies in the world who can do pyrolysis on a commercial basis. Actually, to be honest, that's a pity. We need to have more competition, because only if you have competition, there is a market. Of course, if there's no competition, it also means there's no market. So it's a kind of chicken and egg you have to go through. So we want to do major projects, which I'll come back to later, but I really hope that other companies also start to work on pyrolysis, because it's really, really important. Then yes, second generation. Sustainability we discussed, was already discussed before. It's extremely important. One of the major threats I see now in this moment from my business is the fact that it's not considered sustainable. There was also the word trust. As an industry, we are quite very good in explaining and calculating what we do, but if there's no trust, there's a big issue with our risk to be on this field. So sustainability is absolutely crucial. Now, where we come from?
Technology development is costing a lot of time. BTG was one of the first spin-off companies of University of Twente, where it started in 1987. It's called the rotating cone technology. And it was not a kind of breakthrough. I think, generally speaking, if you talk about innovation, it's always step by step. It's a lot of work. It's maybe 1% inspiration, 99% transpiration. It's really making a mistake, do it again and again. And also this strong belief. I started in this business 10 years ago. When I started, everyone talked about gasification and pyrolysis. Well, it's a brownish liquid which was acid and nightmare. But step by step, pyrolysis get more attraction. All the people at that time believed in pyrolysis. That's what you really need. What is exciting about this picture is not the technology, but the people. It's the people who make it happen. They invented technology. They also improved the technology. And the funny thing in this picture is that all the people you see here still work with pyrolysis, except only one. Only one left us. The rest is still working with pyrolysis. It's the people who do it, and not the other way around. Not the technology. What is fast pyrolysis? Very shortly, what we do is we heat a biomass to around 500 degrees Celsius. We do it fast. That's why it's called fast pyrolysis. When you do it fast, the yield will be the highest. We are a kind of copy of Mother Nature. Mother Nature had more time. Mother Nature had around 200 million years, and we do it in several seconds. Convert the biomass into the oil in 7 seconds. That's not all. We're not only making oil, this is our technology. We are circulating hot sand and mix it with biomass in our reactor. There's a kind of mechanical mixer of the biomass and the hot sand. This is how we achieve this fast heating up. We're creating a kind of oily smoke, and the oily smoke is going to our condenser where it's condensed. That's it. That's the total process. No catalyst, only temperature, and no pressure. A very simple process, else we believe it should be a simple process. No catalyst, no complicated stories, because why? We bring this technology to where the biomass is, close to the biomass. So no hydrogen, no catalyst, no complicated story, it should be a simple one. So decentralized technology to convert the biomass to the crude oil. Then you can transport the oil and then you can do anything you like with the oil. That's the concept. So heating a biomass, getting the oily smoke out, and displaying behind the char. And not throwing away the char, we use the char to drive our process. So when our process is running, we do not need any external energy. That's the advantage of the concept. In our plant and pilot, we're making the oil we deliver to Friesland company, which is a dairy producer, and the heat we are selling to Axelrod, what we call Norwegian. Total efficiency is high, so we are converting around 5 tons per hour in, so every 1,000 kilo of biomass is converted to around 65% pyrolysis oil. And 32% is converted to heat, that's which we use efficiently. Crucial to have an efficient technology. In the past, there was a lot of discussion what is the best technology, what is the highest efficiency. I can tell you it's not about the efficiency itself, it's the total picture. It's more important to have a good price for your heat, for example, than to have the highest yield in your process. That's the total picture which is making it attractive or not. March 2015, first oil was produced at Empire. It's our first commercial plant. And to give you some idea, we made a lot of mistakes and we also learned a lot. And you can see it in this graph. To give you some idea, in the first year, we produced 1,000 tons of pyrolysis oil. And now we're making 1,000 tons of pyrolysis oil per 2.5 weeks. That's a difference. The first year was not an easy year. And to be honest with you, the funny thing was it was not about the core technology, but everything about all those practical, nasty things which are happening when you do something new. Typically speaking, if you would like to use a new technology, it would cost you around 3 years to reach maximum capacity and also a decent amount of handling costs. That's really important. So I will not read everything which is here. Funny thing to say is that the plant is decent scale, 25 megawatt, and 7 operators in total are in the plant. So only 1 operator at a time. We even are thinking to run the plant in night time unmanned. That's also called innovation. It's very important to lower your price and to make it in the market interesting for the market. We sold the plant in January 2019 to Trends. It's fitting perfectly well with our strategy. To be honest with you, there's also a surprise for us that someone else was interested to buy our existing plant, but fitted perfectly. Now we can concentrate on selling technology and do projects, and Trends, which is an operating company, they can really run our plant in Pyro. We still have a 24/7 connection to the Pyro, so we can still learn from the plant, which is crucial. Go back again, March 2015 started with a pilot. Step by step also here, running steadily 24/7. Biomass was certified, crucial. We have the better biomass certificate. It's really considered a residue. January 2019, and Pyro was quite advanced. In April this year, we sold our plant to Finland, GFN. And we just announced in September 2019 that we have sold our plant to Sweden, PureCell. And the exciting thing about the last project is the fact that this oil is used by Cream in their refinery, which is a very big important step, because the refinery sector always have said it's not possible to bring the crude pyrolysis out of the refinery. If you should repeat that to yourself and repeat it and repeat and repeat, then everyone starts to believe. Cream said, no, we believe it's possible. Whereas Petrobras in 2008, 2009 proved it's possible with this pyrolysis oil to a refinery. I am very happy with the brave step of 3. Also now I can see a lot of potential in the market. Other companies also want to explore this route. So there's always a long line for being number 2. And that's why I'm very happy that Cream has taken this very important step. Friesland Campina is using the pyro oil to replace around 10 million cubic meters of natural gas. And there's a total amount of greenhouse gas reduction of around 93%. Commercial rollout. We are very proud that we have sold the plants both in Finland and in Sweden. It's costing a long time. We have to convince the market that things are possible. It's very important to spend time. As I mentioned, you're around 11 years now for the company. And why did they choose for our technology? That's a very important question. Due to the fact that we have Enviro. We have Enviro, we have proven it's possible. We are making oil every day, 24/7. And that's the crucial thing. If you don't have the reference, people have difficulties to report. So both customers, both the Finnish and the Swedish customer, have been 5, 6, 7 times to Enviro, to look at Enviro. We have done a test with their biomass. It's also a possibility in Enviro, if we would have a specific biomass, it can be tested at Enviro. That's also what the customer has done. In both cases, we are using solars to be converted to pyrolysis. BTG BTL is a relatively small company. So BTG is around 35 people, BTG BTL is 10 people. So you can imagine that if you want to do a 25 million euro project, it's a challenge for customers. Okay, I'm giving 25 million to a small company, that's exciting for them. So we decided to team up with Technology Dept. It's a huge contractor in the petrochemical group. And we do projects together with them. So both the Finnish project as the Swedish project, we do it together with Technology. The Scottish Cascade, I like this picture a lot. It's made by BTG. On the left side, you can see the biomass, and on the right side, you can see all types of applications. Low added value, high added value. Typically ask the audience where do you want to be. Everyone said very easy. High added value, that's important. High added value side. I don't want to disagree with you, but how to come there? That's the most interesting question. I think this morning was Patrick mentioned it. It is very important to have an offtake agreement for everything. So if you have a high value added side and you don't have an offtake for the energy part, you cannot run your business. What we do, we start a business with either power applications and step by step valorize. Now people approach and say, could we use the pyrolysis to get some parts out? Yes, it's possible because the residues can still go to the energy sector. Crucial, step by step. So don't begin at the top. It's fine if academia are investigating and researching these routes. But from a marketing perspective, don't start there. Start at the bottom and step by step go. This is the boiler at Campina. Also in Finland it's used. It's to replace, in that case, normal oil. The advantage of Scandinavia for us is the fact there's quite a CO2 tax on fossil. So the fossil can be used without a subsidy by just replacing the oil on a boiler. A very robust application, which I really like. Down to refinery. On the left side you can see our technology. And then there are several ways to go to refinery. The first one is the untreated crude pyrolysis to bring to an FCC refinery under 5%. Easy, that's the first step. If you want to go to higher, then it's better to upgrade your pyrolysis oil. So then you remove part of the oxygen, and then you can go to a higher percentage in the refinery. And step by step, if you go to the MTF, then you are making a complete end product, which is also possible with pyrolysis oil. This is how we do it. This is the cheapest way to go to a refinery, to make second generation fuels. The other thing we need to do is to make a connection on the riser of the FCC and cold feed the pyrolysis oil there. It's an investment of a couple of €100,000, that's it. Just feed it, and then you can see an interesting typical yield of all the different pieces. We have dry gas, there's LPG available, gasoline, diesel, and also slurry oil. Until 5% of this absolutely works perfect. The good thing is, by doing this, oil companies immediately comply with the Renewable Energy Directive. No investment, no couple of $100 million investment. Biomass owners will invest in the pyrolysis plant. The only thing that oil companies need to do is offtake agreement. That's it. Last slide. With respect to time, I'll skip another point. In my presentation, at least I've given you an example of things which are possible at the moment. We are now rolling out this technology. My main markets is especially Europe due to the Renewable Energy Directive, and especially here in Sweden, but also in Finland. It's an excellent market for our technology to start with. Thank you very much.
I have 40 question. What kind of products do you see as your main market and why?
Products? Markets?
Yeah, yes, market products like heat or do you see that for feeding into a refinery as a main market in the coming years?
Yeah, I believe that feeding into refineries, that's our main market. It's supported all over Europe. And the second, also very interesting market here in Sweden and Finland is to replace the normal way. That's a very interesting market. So that's my two main markets, to make renewable heat in the boiler and to go to refineries. Yeah.
Is there anyone having questions from this one, two? Those two questions.
Yeah, thank you for your presentation. Gerhard from Aspen University. I just wanted to check if any kind of using more than 5% of your pyrolysis in your refineries, what would be the problem?
Sorry, can you repeat your question?
So five, at the moment, I think you use about 5%.
Correct.
So any clients beyond 5%?
Did you go? Yeah, if I understand you right, until 5%, it works perfectly because the yields will be the same in the refinery. In the past, people thought if you bring the crude pyrolysis away, your char yield will go up dramatically. That's not the case. The char is even reduced slightly. Gasoline yield goes up a bit, and the diesel yield goes down a little. So, but the yield typically are the same. If you go above 5%, then you're making too much char, and that's the issue. So what you see within pyrolysis oil is the fact that there's quite some sugars inside. So if you bring the sugars directly in too much quantities to an FCC, the sugars will be converted into char. BTG developed a catalyst. It's called a peculiar catalyst to convert those sugars into alcohols. So we believe it's very important step by step. Typical mistake oil companies are making that they say, oh, let's use our standard way, heated the pyrolysis up to 300 degrees Celsius. You can be sure you will be destroying your sugars very efficiently. Absolutely. So absolutely no sense. So first sugars convert to alcohols, and then you can go to 20, 30, 40%. That's the concept. But then you need to understand the way pyrolysis behaves. Oil companies, they don't know. They just have a background of 100 years by pumping things out from the ground. So with oxygen in combination with the sugar, that's the challenge. Can be solved. We do it step by step. Thank you.
The last question, and please keep short.
From NTNU. What is the feedstock flexibility in your technology? How flexible is the technology?
Yeah, we are extremely flexible in the feedstock. We've done 50, 60, 70 types of biomass, but everything has a kind of price. So it's more now a economical choice than a technical choice. For example, sugarcane with us from Brazil is an excellent feedstock. Sunflower, there's a lot of grain, very nice one. Straw can be used. Straw, we started with a project in Denmark. I can tell you straw would be possible, but the problem is straw is quite expensive. The straw in Denmark at that time was around 100 euros per ton. If that's your starting point of your project, then you can be sure you won't have any project. And let's say the sawdust here in this area is a lot cheaper. So it's more an economical choice. Typically speaking, pyrolysis technology is very feedstock flexible technology due to the fact that we are running on 500 degrees Celsius. So especially ash melting, which you have is the potassium you don't have. That's the advantage of pyrolysis.
Thank you very much. Gerhard Muggen.
Thank you.
And I have a gift for you. Let's dive into the research. Karin Pettersson from Research will walk us through economic aspects of biofuels.
Yeah, thank you very much. I will present this project called Real Cost for Forest-Based Biofuels, which was finalized earlier this year within the research program Renewable Transportation Fuels and Systems, which we introduced earlier today. and was conducted as cooperation between RISE, where I work, and the consulting company Sweco. So the primary aim of the study was to estimate the well-to-wheel cost for forest-based biofuels. And we focused on road traffic and usage in different segments in road traffic, and we compared it with fossil fuels in this context. And this comparison that we did, which was based on the end user, illustrates how different renewable alternatives can compete with fossil value chains, and under which conditions there is a potential for profitable biofuel production. So based on previous studies, we selected 4 different concepts for production of advanced or second generation biofuels. Methane or SMG, gasification based, gasification. Methanol produced via black liquid gasification. Concept with ethanol and biogas. And a concept with renewable petrol and diesel from bio-oil, all integrated into existing industry to increase both energy and economic efficiency. And when it comes to uses, we considered 3 different transport segments. Here I will focus on the car segment as well as the long distance truck segment, but the results for the distribution truck are similar to the long distance truck. So shortly about what did we do and the main assumptions. This is the type of results that I will present. So the total well-to-wheel cost here, 2 examples with methanol and biopetrol for the car segment. And we indicated the cost for production, distribution, and vehicle, and compared it to a fossil reference. And one thing is that for this fossil reference, we included margins for the producers and distributors. It's a total well-to-wheel cost for the end user. But for the biofuel chains, we didn't include any margins for producers and distributors. Instead, it's sort of a result from the comparison. So if we assume that the end user will have the same cost for fossil alternatives as for biofuel alternatives, we have an indication here, do we have any potential margins for producers and distributors of biofuels, assuming that the end user should have the same cost. It's complicated to take it so short and so many assumptions, but we use current market prices in this study as well as the current policy situation in Sweden. But we have a time perspective that is 2030. So we, for example, assume that the technologies are in place, so to say, that they are commercial, and we have assumptions regarding, for example, plant's performance. So that's quite important to stress. And we looked at high blend or pure biofuels, so not drop-in. We consider all biofuels we study as high blend or pure biofuel, which in Sweden means that they have a tax exemption, so they don't pay the CO2 tax nor energy tax. So moving on to the results. Here we can see that total well-to-wheel cost for the studied value chain for the car segment, and for those production concepts containing 2 different biofuels, we sort of present the result per biofuel using energy allocation to make it more transparent. We can see here for the car segment that the dominating cost is the vehicle cost, and dominated by the actual purchase cost per vehicle divided into cost each year then. And all you can see here, if you compare this first 5 months to fossil petrol and biodiesel to fossil diesel, we can see that all biofuels are competitive. And we have actually significant margins for producers and distributors. Maybe a margin in crowns per kilometers doesn't say that much. So if we convert the margins to crowns, which are approximately 10 crowns, so it's €1, to crowns per kilowatt hour biofuels, we have a margin between 0.2 and 0.45 crowns per kilowatt hours for the different biofuel. And then how important is this tax exemption and the energy and CO2 tax? It adds about 0.7 crowns for petrol and 0.5 crowns for diesel. So then one can conclude, looking at the numbers here, that without this policy instruments, the biofuels are not competitive compared to fossil fuels. In the study, we present results both with and without policy instruments, so we make that the effect clear in the report. I have not the time to show all the results here. But in addition to the sort of sensitivity analysis when it comes to policy instrument, we did quite an extensive sensitivity analysis for a number of factors. The one shown here is actually the one with the largest impact, and it includes, for example, the biomass price, the crude oil price, and how you price the excess heat from the biofuels plants that are sort of used at the host industry. But we can see here that most alternatives are still competitive, and we still have significant margins even when we change this parameter, sort of an unfavorable direction for the different alternatives. But we can see, for example, that this biodiesel, it's quite sensitive to changes. But we included the sensitivity analysis. We combine a number of factors, but still, then we have a positive margin for almost all the alternatives studied. Moving on with the long-distance truck segment and the results there, and the total well-to-wheel cost first. The first thing we can see is that the vehicle cost here is less dominant compared to the car segment, and I mean the reason for that is that the average distance traveled by a long-distance truck each year it's much longer than a personal car, and of course then the variable cost becomes more important for the truck segment. And also here we can see that all biofuels have lower cost compared with the fossil reference. It might look like that the margin is bigger here, but it's in crowns per kilometers, and as we use more fuel, so if we convert it to the next slide, we can see that methanol and ethanol here have the somewhat lower cost than the other biofuels in the segment. It was more in the car segment. But if we convert it to crowns per kilowatt hour biofuel, we have similar results really to the car segment, between 0.15 and 0.45 crowns per kilowatt hours. And since we have a more sort of the fuel cost or the variable cost have a more significant share here for the truck segment, I mean the results are also more sensitive to changes of those parameters. And for example, here we can see that both the biogas and biodiesel value chains have sort of small or even negative margins for some of the parameters studied in the sensitivity analysis. So yes, moving on to the summary and conclusions. All the studied value chains or biofuels considering this study have the opportunity to be profitable with the current policy situation in Sweden. Here's just a Summary showing the margin for both the car segment and the long distance truck segment. Looking at the specific biofuels, methanol and ethanol actually have the highest average potential margin for producers and distributors, which is also very stable looking at different transport segments. But also SNG and biopetrol have very high potential margins. I can say something about the size of the margins because you can relate them to the production cost for the biofuel that we estimated here, which is between 0.5 and 0.85 crowns per kilowatt hours. And also the Swedish Energy Agency estimated the margins for production of fossil petrol and diesel to between 0.1 and 0.15 crowns per kilowatt hours. And also biodiesel and biogas have a somewhat lower but still relatively high margin, but they are more uncertain, and when changing certain parameters, they will have very small or negative margins. And if we look at the production processes, which is in some cases then a combination of different biofuel, it's the methanol, SNG, and ethanol biogas concept that all have significant margins also when parameters are changed radically. And this is not the case for the biodiesel biopetrol process. Okay, thank you very much. I posted a link to the report, which includes more than what I have presented here. Thank you.
Very nice presentation and very optimistic on the.
Yeah, I agree. But I can also I said a bit about that in the assumptions. But I can also add that I mean, as I said, we assume that the technologies are in place, that there are no additional risk for the biofuels concepts compared to the fossil ones. I mean, it's not mirroring the situation now. How do we get the first sort of big commercial plants in place? That's another question. And as Ingrid mentioned this morning, we in Sweden have policies directed to the usage and not the production, which is the big problem for these type of production plants.
That's kind of same as in Norway. In Norway, now the biofuels are not that exempted anymore. What do you see as the other kind of, how can you promote biofuels without that? Are there any of your biofuels that could survive without the tax exemption? Because you mentioned that that was single most efficient.
Yeah, and of course that includes an exemption from both CO2 tax and energy tax. And of course, I mean, an exemption from CO2 tax I see is more, I mean, that's more sort of natural, but I mean, you could reduce the tax exemption and still have quite significant margins actually. What was your question? But I mean, of course, you need some kind of support or something for the coming future. Even if it could be a bit lower, maybe than it is today.
Yeah, very good. Are there any questions from the audience? Everything was clear? Okay.
Olaf from Swedish University of Sciences. Can you elaborate a little bit on the production costs? They look quite similar for the different fuels.
Yeah, they are quite similar. As I said, it's in the range between 0.5 and 0.85 crowns per kilowatt hours, and it's lowest for the SNG process and highest for the biopetrol biodiesel concept, and the other ones lies in between. So it's the production cost we estimated using current market prices for both biomass other chemicals. And we then assume, as I said, that integration is a very important issue here. All the processes are very sort of energy efficient, integrated into existing industry, and also, of course, that reduces to some extent also the capital investment using existing infrastructure, and also sort of replacing their need for investments in new heat and power capacity.
Thank you very much. And now we have the next one with the Bioethanol, replacing Olaf Trygve Berghlin, and he is going to walk us through how to distillate the ethanol in a hybrid process. Looking forward to it.
Thanks for the introduction. My name is Bernd Wittgens, working for SINTEF as a senior advisor, and as Judit said, I'm replacing Olaf Trygve Berghlin, who's supposed to give the presentation. The previous presentation was basically on overcosts. Now we try to find out how to modify the process, reduce the production costs. The outline, how is ethanol produced? We need to get rid of the water. What kind of experience we have done? And how to integrate two completely different processes into one process, which makes it better. And then some conclusions in an outlook. Bioethanol is produced by converting some substrate into hydroside, means make sugar, run them through a fermenter, and then current technology is we use two distillation columns, first the beer column and the rectification column, and then we have to get rid of the rest of the water by a, for example, molecular sieve process. Those processes are relatively well known. They have one challenge: they are energy intensive. When we want to have fuel, we would like to have 99.5% weight of ethanol. The problem with ethanol and water is you can, by distillation, only get to a certain point, and then you can't separate it anymore. So you need to have a second process behind that. We looked into that, and we had a project actually which started on, you have a bioreactor, put the membrane system into the bioreactor, get the ethanol out of it. Very nice idea, don't work. It's that simple. So what we need to do is we need to find alternative way to do that. So we went back to our initial idea. We run the distillation for the first part, and then we take a difficult separation part for other processes. And we looked into 5 alternatives. The interesting part with these 5 alternatives is it brings you from your physical limit, which is the azeotrope, to your fuel concentration. But then we found a paper from 1987 which looks into distillation or separation problems. In 1987, it was stated that this separation technologies, these were kind of mature, so like distillation, absorption, azeotropic distillation, and membranes, they were very much down here. That means they are not mature technology, technology maturity was limited. Today, we are more or less at the same place. But that is if you use one process at a time. A little bit to membrane separations. What's the problem? The problem is very simple. If you run a evaporation process, that means you drag ethanol as a vapor through the membrane and you put it into broth. You have particles in your broth which follow the membrane. That means it will clog in no time. You have a very poor driving force. If you come, let's say you start with 5% ethanol in a water mixture, which is standard for a fermenter. You want to get up to 70 to 80%. You use a lot of energy for that. And your product, ethanol, has to be condensed at a very low pressure. That means you need a very low temperature, which costs, again, a lot of money. So that baby, it doesn't work. So when we run that project, we ended up with vacuum pumps which need to be operated at 20 millibar absolute pressure. Every engineer will say that costs a fortune. The other part is if you want to condensate your ethanol at 20 millibar, it's even more expensive. So we put that to the side. And then we looked into, can we make a trade-off of our driving forces? So we came up with a very counterintuitive idea. If you increase the pressure in the distillation column, your separation gets worse. But on the other hand, if you increase the pressure, we have a higher driving force for our permeation process. So balancing these two is basically the key what we've done. So we built a small system, used commercial membrane for perforation, which is actually not designed for that process. The membrane is designed for feeding a liquid into the membrane system and drying out vapor. What we did, we feed vapor into the membrane, which Bioethanol told us in the start it is not possible. Of course, we tried, and surprisingly enough, it worked for quite some time. See the operation times, we operated it for about 125 hours. We get quite a high flux through the membrane, and then our membrane break down. And that was because we run the system up and down all the time, and membrane is not made for that. So we, as first previous presenter said, we learn from our errors. So we made another system which we operated in a different way, and that worked for quite some time. So how the process looks like? We still have a distillation column in the start, and then we exchange the second separation column, the dewater and the dehydration section, with one membrane section. So we basically reduce more or less 60% of the process capital costs. They're removed. So we get a much simpler process. Okay. And why is it much cheaper? Because we generate our pressure by pumping a liquid. This costs close to nothing. Compressing a vapor is relatively expensive, especially if it's a vapor which additionally condensates, which makes it even more complicated. So then we run the energy analysis of the two processes. We compared them. We used data from an NREL paper from 2011. They have two distillation columns, a molecular seed section, and the separation costs about 7.4 megajoule per kilogram, just for the separation costs. We leave out the cost for the feedstock or the fermentation, just to make it simpler. In the process we developed, we have one distillation column, a gas permeation membrane. The data we get from Palvatech and our own data are about 9 kilogram per hour per square meter membrane, which is quite large compared to the original data, but that's because we feed in a vapor, not a liquid. So we reduce our energy consumption by about 18%, which is quite substantial because the distillation is a major energy consuming part of the process. So if you get down this energy consumption, it also reduces your operational costs. Conclusions? Integration of distillation and evaporation. It's a classical process intensification approach. You take the simple part of the optimal operation range of two processes, integrate them, and you get a much better process. However, we have to make a trade-off. We have a trade-off between the separation efficiency in the distillation column and increase the gain or the driving forces for the permeation section. So it's not straightforward. You have to play with it and have to find the right combination. It's a very much simplified process because those membranes will never ever foul. All the fouling is happening in the distillation column and beer column, and that is handled in industries. We have done that for about 2,000 years to produce alcohol for drinking, so that problem is quite easily solved. We have a much better energy performance with the scheme we designed. we have lower or comparable lower capital cost with the proposed scheme. But there's a drawback. It works only for processes where we have a low boiling alcohol, a low boiling liquid. Our solvent is water, which has a 100-degree boiling point. Ethanol has 78.4 degrees, so that works nicely. If you were to like produce butanol, it will not work. Butanol is 170 degrees, so it's a higher boiler than water. So we need to play with that a little bit more to see if we can use that in the same way. Where the challenges are outlook, the membrane modules today, they are relatively costly. And as you've seen, they have a tendency to crack. So we need to make them more robust and we have to reduce cost. And also we need to perform a rigorous technical and economical evaluation. And that is ongoing in the biofuels project. That concludes my talk. And I will be happy to answer your questions.
That was big.
You asked me to stay on time. So.
Thank you for that. Very interesting. My question is, how, where you are at this TRL scale, how far is it from real commercial value?
None of the systems is, everything is industrial scale. It's just the integration of the systems which is different. So basically, each individual process is TRL 9. Integrating of them, I haven't seen that in industry, but it has been done in pilot runs. But therefore, a different application. Because what you do is, in the preparation step, you're not separating the alcohol from the water, you separate the water from the alcohol. So you drag the water out of the system, which is, after you distill it up to 60–70%, this is the simplest way. And those membranes, they are readily available. You have all of them, and they are relatively cheap. But the integration has not been done so far.
Do you see a potential of retrofitting existing?
Yeah, definitely.
Okay. Any questions from the audience?
It all sounds very convincing, so I was just wondering why has it not been implemented?
To cite someone from industry, it works with 2 distillation column and pressure swing absorption, because that is the standard today, and you have standard boxes to just build them. No one is actually looking into that, and the other part is currently there will not be built too many bioethanol plants. The 2 which are currently in construction, they use pressure swing absorption because it's kind of the industry standard. The problem is to get that into industry and get industry to think different. So we need probably new engineers to go into industry and show them what is possible. And I believe you have experienced more or less the same. You get the standard solution, and if you ask for something different, it's like, sorry, no guarantee. I don't give you a price.
Okay, thank you very much. Okay, next speaker will be Jin Xuan, and he will speak about model-based cost screening, electrochemical reaction pathways. I'm looking forward to it.
Thank you. Okay, thank you for the introduction. So good afternoon. My name is Jin Xuan from Loughborough University, UK. So I'm here representing one of the Super Jim projects was awarded last year. So my research was a little bit at a lower TRL compared to the previous presentations. And typically, my presentation was the research was beyond the TRL 1, 2, 3, so we have frontier. And I will talk about the electrochemical process. So some of you may not be familiar with the electrochemical process. It plays a very important role in renewable energy, like battery, fuel cells, water splitting to generate hydrogen. But today I'm going to talk about the use of electrochemical processes in generating biofuels and at the same time to reduce the carbon dioxide. So I'm here, as I said, I represent one of the Supergin and the Department for Transport jointly funded project last year. So the project is called eBiofuel, and I'm the principal investigator. It also involved Dr. Jin Xuan from Harvard University. Unfortunately, she cannot be joining today. So the project started early this year in April, so it's only like 6 months from the starting of the project. So the results I'm going to present will be preliminary, but hopefully from my presentation I can convince you that the technology we propose is a quite promising one. So the Supergin, the Bioenergy Hub and the Department for Transport released a call for this flexible grant, and they asked us particularly to look at the bioenergy together with CCUS, carbon capture, storage, and utilization, because the BECCS of CCUS is one of the very few solutions that can provide the negative emission energy supply. So if we think bioenergy is a neutral to slightly positive carbon emission, then bioenergy with CCS or CCUS will give us a solution of neutral to negative carbon emission. So we don't need like the entire national energy supply to be carbon negative, but if we want to achieve the net zero emission by 2050, we do need a proportion of energy supply to be carbon negative. So this diagram I draw from, I extract from the CCC report. So the story is by 2050, the UK want to achieve a net zero carbon emission, and whatever low carbon solution you provide, you still have some residual positive emission. So we do need to develop the negative emission technology to offset this type of carbon emission. And from the CCC report, the bioenergy with CCS has represent a significant proportion to remove this residual positive carbon. And as you can see, there's still a blank area here that at the moment we don't know how to deal with this carbon emission residue, which means probably we need to develop a little bit and move forward the state of the art of the bioenergy with CCS to enhance the potential so that it can cover more carbon emission to offset more carbon emissions. So as I said, biofuel with CCS will play a very important role in the UK's emission removal and offset. And so with this content, we propose a so-called e-biofuel-based circular economy concept. So the core is to use the electrochemical process to develop biofuel at the same time to reduce carbon dioxide into useful fuels. So if we start from renewables, biomass, or the waste through different bio-based process, for example, fermentation, then you will probably get some intermediate like carboxylic acid, and those intermediate itself is a useful molecule, but sometimes, or in most cases, we want to upgrade it into fuels or more value-added chemicals. And we can do it through electrochemical process with the input of renewable energy. For example, we can get more energy-dense alkenes from the carboxylic acid. And the fermentation process will generate quite a number of carbon emission, and of course, the end use of the fuel will also generate carbon dioxide and waste. So if we integrate the carbon capture and to use, again, the electrochemical process to convert the carbon dioxide into something useful, typically methanol, ethanol, formic acid, whenever possible, then you can get at the same time two types of fuels, two streams of fuel production on the same electrochemical unit or process, and then you close the loop of the carbon to achieve potentially sustainable and negative emission. So I would elaborate a little bit more about the fundamental science and chemistry behind this idea. So as most of you know, that the electrochemical process typically involve two types of half cell reactions, the anode and the cathode. So one is oxidation, other is reduction. So if you want to reduce the CO2, so the CO2 is a reduction process, which means at the cathode you reduce the CO2 into some fuels like methanol, typically methanol. And it has to be accomplished with a oxidation process. So most typically is the oxidize of water to generate oxygen. And the only useful part is this part, but more than 90% of the energy actually is used to overcome the water oxidation. So only 10% of the energy would actually use for CO2 reduction. The same for the biomass valorization. So it can be both reduction and oxidation, but here we talk about the oxidation, for example, typically to oxidize, selective oxidize the CAs into alkenes. And then you need to accomplish with another half cell water splitting. Again, more than half of the energy was wasted here. And with the present generation also generate problems in this kind of systems. So our idea actually is to get rid of the unuseful part and combine the useful electrochemical reactions. So to generate this, the new e-biofuel system or biofunctional electrochemical system. So at the one side, we reduce the carbon dioxide to methanol, and at the other side, we selectively oxidize the CAs into alkenes, so that we maximize the usage of electrons, the energy in the electron flows. And the chemistry underpinned this new process has been somehow cool. For example, last year there's a paper published in Andrew White about to oxidize the middle chain carbonic acid through the electrochemical cobalt reaction to the mixture of alkenes, and it can achieve quite high energy efficiency, like 80%. And at the same time, we can also reduce carbon dioxide. This is our own work published last year. You can reduce carbon dioxide through electrochemical reaction into carbon monoxide or formic or methanol. So this project is essentially to use this chemistry and to build a novel process that can at the same time do the two jobs. So it's a synergistic integration of the anodic carbonic acid upgrading and the cathodic CO2 reduction. And the ultimate goal is to intensively reduce emission and increase the sustainability of the road transport sector. So we want to build road transport fuels through these new processes. So throughout the last 6 months, we get some initial results. So the project proposed into 3 work patches. So the first is about the experimental work to prove the concept. So we use the very state-of-the-art electrochemical cells to study the fundamental electrochemical kinetics. We actually did more than we proposed. So we screened a series of anodic oxidation processes, like different bio-based molecules, not only the organic acid, but for example, alcohols or even methane oxidation to energy-dense fuels. And at that case, we screened the CO2 reduction, but also other options like SO2, methanol reduction, etc. So we did generate some exciting results, and we believe that some of the results can generate patentable IP. So with the help of the University Enterprise Office, we are currently engaging with the Midland Innovation Micron. So we are very likely to get another grant of the funding more focused on the commercialization side. So because of this, I cannot disclose too much technical details because we are looking at a patent later. And then the second work pattern is about the modeling part. So we developed a numerical model actually to screen a number of reactions. So the model is first, of course, validated against experimental data. And once it is validated, we have extra information from the literature. So we have selected 20 anodic and 10 cathodic reactions, so different options, all from the literature. And we supply the kinetics data into the model, so it will generate results, performance results, and we can see which one is better than the others. So here are some results of discussion. So this is a typical CFD model on the electrochemical reactor, so that you can generate the characteristics of a mass transfer and also the electron transfer. And because of time, I don't want to go to too much details, but I want to show you what we have been screening. I mean, the criteria we use to screen different type of reactions. So the first is about the energy efficiency, because this process did involve the renewable energy input. So we want to see the cell energy efficiency. So you can see some are more efficient than the others because of the inherent kinetics. So some are much easier to be performed. We also look at the CO2 removal potential. So eventually we want to remove as much as CO2 from the reaction. So we look at the number of CO2 reacted over the number of CO2 fed. So you can see quite a number of reactions options can reach more than half CO2 removal rate. Some are higher, some are lower. But if some reaction did generate more CO2 than you supply, so you get some negative value. So this probably what we want choose these kind of options. And we also look at the E factors. So this is about environmental or the sustainability, the waste generation from these kind of reactions. At current, the E factors are all quite high because we didn't cycle the solutions, but it can be potentially lower in a later stage. And we also look at the economic analysis. We want to compare the value of the product to the value of the reactant. So again, it varies very much. So some reactions will generate a very high value added product, while some, when you do the reaction, you are losing money. So far we have gone through this type of criteria, but we haven't made a decision which reactions we want to go. So this is about the work package 3. So Dr. Jin Xuan Karin will use a multi-criteria, multi-objective optimization or decision model to help us select the best reaction to go forward with consideration of all these criteria. And last, at the end of this project, we will have like a workshop associated with this project to talk about green finance, energy economies, and sustainable finance. So the idea is at that point we will have some more solid data, so we want to engage with the business side of the sector to find the ways to commercialize our technology. So finally, I would like to acknowledge the Jin Biology Hub and the Department for Transport to provide this funding to do this exciting research. Thank you very much.
Thank you very much for a very interesting presentation. It was very basic science for me. What can you say about how long will it take to commercialize? Do you see that it can be commercialized pretty fast?
I don't see it will, to be honest, it will commercialize really fast. So we are talking about TRL 123. So this is typical research funded by the UK Research Council. So if you look at that low TRL level, then I don't see there will be like immediate opportunity for commercialization. And also, this process depends on the carbon capture process to be in place. And I don't think there will be any carbon capture in the UK in the next 5 years. So ideally speaking, I think there will be some impact within the next probably 5-10 years. That's very optimistic.
But it will be probably a good solution for a small scale.
Yes.
Where you can that. Okay, we have one question from the audience.
Hello, Jin Xuan, SINTEF Energy. I've never come across pounds per mole before. Call me old-fashioned, but for the methanol, well, it's about 350 pounds per tonne. Have you done the calculation in pounds per tonne of what the methanol would be, for example?
Yes. So currently we just simply compare the price of the product with the price of the reactant, and the price are taken from like the key chemical supplier like Sigma Aldrich. So probably it will not precisely represent.
I would use Alibaba.
Yeah, okay. Yeah. So we currently use Sigma Aldrich. So it doesn't fully represent the picture because if we talk about the bulk, a larger volume, then the price may change. But it gives us some sets which are cheaper, which are more expensive.
But just think about some of the big, you're looking at bulk compounds, especially when they do carbon capture, where the commercialization will sort of stand on whether or not it's interesting or useful. For it to be useful, then you've got to think about the alternative costs for sort of unicorns like direct air capture and other things. So, what is the, how many pounds per ton CO2 avoided or some calculation like that? That will get the interest. So pounds per volume.
Yeah. So yes, so this is something exactly in our plan. So I think the cost associated with CO2 capture was there. So we are not dealing with any like innovation on CO2 capture itself. But we are really when the CO2 is captured, we want to use what there's cost associated with that as well. So currently we only compare the cost between product and the reactant. It does not reflect the cost actually in converting because some reaction needs more, for example, more expensive catalyst. So this is the cost analysis we are going to do in the next stage.
One last question.
Thank you for your presentation. I don't know. Do you mind going back a few slides? It's technical question I would like to ask.
Yeah, which one?
No, please go electronics.
Which one?
No, keep going.
This one? No? Okay. Which one? This one?
Yeah, here.
Right.
So what reactions actually require the use of hydrogen? Where does that come from?
There's no hydrogen. I mean, so the story is, I mean, if you want to do an oxidation reaction, for example, to selective oxidize CAs into alkanes, then you need to split. There's a reduction reaction associated with that. So normally people do water splitting, so you generate hydrogen from there. So I mean, you see that's hydrogen, but at this low volume, you cannot make money from that. It only induces dangers to the system. So we remove this part. So basically, it's this bit combined with this bit. So to form the new system. So there will be no hydrogen generation in the new system.
Yeah. To change the carboxylic acid to an alkane, you're adding hydrogen. Where does it go?
Yeah, so it can be from the water. So
the causal reaction is decarboxylation on top of an oxidation. That's why it looks strange, but it's right.
Thank you.
Thank you very much. Okay, last presenter for this session will be Dumitrita Spinu from NTNU, and she will talk about catalytic vapor upgrading after fast pyrolysis of lignin.
Okay, my name is Dumitrita. I'm coming from NTNU, and actually I'm a new PhD candidate at Norwegian University. But today I'm going to present some interesting results from my master thesis. That was entitled Lignin to Biofuels via fast pyrolysis process assisted by the volatiles catalytic upgrading. So I will go through two types of reactors. It's a micropyrolyzer and it's a fixed bed reactor. And I will also present some results based on different zeolites that I used in my process. So, as all the people mentioned before, CO2 is indeed a huge problem on our planet. and also the depletion of the fossil fuel. But we also have to think positively, because fossil fuel is actually a source that can help us to give energy and to find new solutions, to find new renewable sources. So in my presentation, I will focus on the biomass, and we have the first generation biofuel. But we also have to consider that we are so many on this planet, and this one is not anymore an option because we have the food competition. And we also have the second generation that is based on the lignocellulose, and also the third generation that is algae. The third one is also interesting, but I will focus on the lignocellulose and especially the lignin that was supplied by SP1 company. And yes, in my presentation, I will try to actually combine the lignin and maybe to actually provide a solution, and also by using the fast pyrolysis that was presented by Gerhard. So this is the lignin structure. As you can see, it's a very rich source in the aromatic compounds, and this part is the most abundant in the lignin structure. If we extract this element in the fast pyrolysis by retroactive reaction, we actually decompose in the compound B and C. The C, through tautomerization, is converted easily into the guaiacol. However, the compound B can be converted in different products like vanillin, guaiacol, creosol, aposonin, and many other products. As you can see, they are very similar. They have this hydroxy and methoxy group. The main difference is the side chain in the para position, and actually all this, they can give CO, C1, unsaturated, and saturated C2 and C3, as well as CO2. From the methoxy group, we can produce methane, as well as CO and CO2, and from the hydroxy, we can produce hydrogen and water. So, as I mentioned, in my master thesis, I used two types of reactors. It's a pyrolyzer connected with the GCMS and a fixed bed reactor. So actually, the micropyrolyzer is very interesting to actually screen very fast different temperatures, different catalysts, but it's not very useful if we want to have a view of the quantitative analysis. We only can see what we can produce, but we are also interested in how much we can produce of this biofuel, solid, and the gas. So this is the micropyrolyzer. It can use up to 0.5 milligrams of lignin in one run, and we have the fast pyrolysis that is the lignin and the quartzol that keeps the biomass inside, and we have the ex situ process. Here we have the lignin, the quartzol, and the catalyst. So we first generated the vapors in the fast pyrolysis, and then the vapors go to the catalyst bed and they upgrade it. That's why we call it catalytic upgrading. In the fixed bed reactor, that is actually a tailor-made entrained flow fast pyrolysis. Here we have the catalyst bed that is between the two quartzol. So we insert the lignin from this point into the reactor. We have the fast pyrolysis, and then they go through the catalyst bed. So actually, this piston mechanism, I use it in my master thesis, but we changed a bit the design of the reactor, and now we have two ball valves, and between these two ball valves, we have the lignin. We can pressurize the space between these two valves. So the pressurize up to, let's say, 1.5 bars can help us to flush the lignin inside the reactor, because biomass, it behaves like an electrostatic material, and it's every time it tries to stick on the wall, and it's not really possible to flush it out inside the reactor. So actually, by doing this, we actually, by opening the second valve, we insert the lignin in the reactor. By closing it, we can charge again the upper part of the reactor. So in this way, we can actually assure the semi-continuous way of feeding. And according to this, we actually can have kinetic inside, and also to study the deactivation of the catalyst. In this part, we have the condenser, and here we have the gas collection that is further analyzed by the GC, FID, MS, and TCD. So these are the results from the micropyrolyzer. As you can see, we produce a lot of phenol alkoxy, and they have this structure, the hydroxy and methoxy group. So we have a lot of oxygen, and we don't want, because this actually increases the rate of polymerization, and the oil that contains oxygen is very acidic. So we have actually to extract the oxygen from the molecular structure. And by increasing the temperature, we actually increase the phenol. And the phenol is obtained by just breaking the methoxy group. And we also can produce monoaromatic hydrocarbons by just also breaking the hydroxy group. So in my next slide, we also tested the different zeolites. And here we can see the ZM5 with the different acidities. The number means the silica-alumina ratio. So a higher number means a lower acidity, or a lower number means high acidity. So as you can see, higher acidity actually promotes the formation of monoaromatics as well as the aromatic hydrocarbons. Compared with 280 that actually produce a lot of phenol alkoxy, and we don't want this product in the final product. So we also tested the ZM22 because it has similar pore size like ZM5, but it doesn't produce so much monoaromatics and diaromatics. We also studied SAPO, but it has much smaller pore size compared with ZM5, so actually they are not able to convert it because the large compounds, the oxygenated compounds, don't fit into the pore size. We also tried to analyze the pore size influence, as ZM5, H-beta, and HY, they have a big difference in the pore size. As you can see, by increasing the pore size, we actually promote more diaromatics than monoaromatic hydrocarbons. While HY has quite the same product distribution as ZM5. And this is because of the structure of the catalyst. Yes. And here you can see the super cage of the HY that actually has very strong acid sites in this super cage. And this super cage, they actually promotes the formation of the coke. So this part we want to avoid. And if we shift to the H-beta, it has a bit smaller size, 0.8. That's why it promotes the formation of these diaromatics and polyaromatics compared with the monoaromatic hydrocarbons. If going to the products distribution, we can see that the monoaromatic hydrocarbons is mostly toluene, benzene, paraxylene. In the diaromatics, we have naphthalene, we have 1-methyl naphthalene. And for the polyaromatics, it's the fluorine. So, the fixed bed reactor, the in-train flow pyrolysis reactor. Here we can see how much gas we produce for the fast pyrolysis and fast pyrolysis with the catalytic upgrading. And based on the weight percentage, we can see that we a bit in the catalytic process, we produce a bit less liquid. And this is because using the catalyst, we have a cracking of the side chains, so we produce more gas and a bit less liquid as the molecular weight is lower compared with the oxygenated molecular weight. And as you can see, the mass balance is not complete, and this is because we still struggle with the lignin and its electrostatic behavior. So yes, it's a bit challenge, but we are working on the design of the reactor, so hopefully we'll manage to increase the mass balance and to close it. If going to the gas products, we produce a lot of CO, and this is because of the methoxy group, the ether groups that we have in the lignin structure, as well as CO2. And we also produce saturated and unsaturated C2, C3, methane, and a bit of hydrogen. If going to the products distribution, we can see that by using the catalyst, we actually shift the oxygenated molecules to the unoxygenated molecules that are aromatic hydrocarbons. And compared with the micropyrolyzer products distribution, we produce the same compounds, and also the monoaromatics hydrocarbons are in high content as well as for the fixed bed reactor. Going to the conclusions, because of the similarity of these two reactors, actually, we can say that the tailor-made entrained flow reactor is quite promising to have an insight of the qualitative and quantitative analysis, as well as we can use it for the study of the deactivation of the catalyst and also the kinetic, that is very important. And also from studying different types of the zeolites, we can conclude that ZL5 is still a promising catalyst because it has the proper pore size to produce these monoaromatics, and the pore size as well as inhibits the formation of the group inside the catalyst. Yes, thank you very much, and acknowledgement to the ST1 as they supplied the lignin and also maintain the collaboration with the NTNU, and also to the Research Council of Norway.
Thank you very much. So just a quick recap. Your aim was to remove the oxygen. Yes. Did you measure the catalyst deactivation rate or lifetime of the catalyst?
No, because in my master thesis we actually changed about the design of the reactor. So I was focused more time on the reactor, and then we didn't have so much time to test also the deactivation of the catalyst. But currently we have another master student that is working on lignin, but also on the fine, and also maybe of the coping of these two. So maybe to the next conference you will come and present your results.
Looking forward. Are there any questions from the audience? No. Okay.
Thank you very much.
And I have a couple of practical info. First of all, I would like to thank you for all the presenters to the wonderful presentations. I think we have learned a lot today. So thank you. If you want to talk with them, I hope you will be available later on. So thank you for all the presenters. And now we will have a short break until 5:15. We will have a poster session combined with dinner. The dinner will be out here, so you can go through all the posters and look the presentations over there. Yes? So let me just repeat it in case if someone wants to submit to the special edition of the journal, Patricia will be out here until 5:15. So, yeah. Thank you very much. Thank you.